the opportunity to talk here today. I'm going to talk a bit about torsion cosmology and some recent developments we've had in this. So I'll first give a sort of lightning introduction to what torsion is and why we might want to consider it. We're used to dealing with Einstein's gravity, so we just have a metric tensor, and the affine connection you want to put on that is just going to be built out of that metric tensor in a very concrete way, so that's a Levi-Civita connection. But there are other ways to construct gravity theory. So one of the more prominent ways is to split the metric into its square root, which is a pair of tetrad fields, so B and H here. And you can also have the connection free to vary. And the way we do that is we introduce this field A, which is a spin connection. And if you do that, then the final connection you get on the theory is going to be Levi-Civita plus something else. And that something else is called the contorsion tensor. And that's where the torsion comes from. So it's just by adding another set of degrees of freedom to the theory. So in Einstein's theory, we only really have one field strength tensor, which is the Riemann curvature tensor. If you have tetrads and a spin connection, then there are really two field strength tensors you can get. You can get a Riemann-Cartan curvature, and you can get a torsion tensor. And these differ quite distinctly in a structural sense from the Riemann curvature. So Riemann curvature has second derivatives of the metric in it. Riemann-Cartan and torsion tensors, they have first derivatives. So why would you do any of this? Well, if you want to couple a gravitational theory to some fermions, then you're going to need a set of Lorentz indices. So those are in Roman letters. And that's what the tetrads are for. They're basically to facilitate coupling to spinors. Once you've done all of this, you end up actually increasing the symmetry you've got at a very fundamental level in your gravitational theory. So Einstein's theory has this symmetry of changing the coordinates. So you've got this diffeomorphism variance of the theory. If you include the tetrads and spin connection, you can rotate your local Lorentz basis. So you're introducing Lorentz rotations into the symmetry group as well. So you end up with a gauge theory of the whole Poincare group. And so this thing is called Poincare gauge theory of gravity. And it's really old. So I've got some references down here. It's getting on for 70 years old now in its various forms. And a nice thing about this is the field strength tensors that you're dealing with. As I say, we go from the second order formalism with the Riemann curvature. We've gone over to first derivatives of the gravitational potentials, spin connection and tetrads. And you've also got these inhomogeneous terms on the end here, which look like the structure constants. So this is very similar to sort of Yang-Mills kind of field strength tensors that you might see in the standard model. But we still don't actually have a theory, so we need to set up some kind of Lagrangian. In Einstein's theory, this is obviously very simple. We just pick the scalar part of the Riemann curvature. So this is the Einstein-Hilbert action. If we're building things out of Riemann-Cartan and torsion, then one option is to just follow the Einstein route and use the linear, the scalar part of the Riemann-Cartan curvature. So this is what Einstein-Cartan theory. There is another option, which is you build a Lagrangian out of the quadratic invariance of the torsion tensor. So you can come up with this thing called teleparallel theory. And the reasons that these theories are so popular is because they happen up to various caveats to be dynamically equivalent to general relativity. So there are various problems with how far that equivalence goes, but for things like free fields, it's fairly sound. So in this talk, we're going to go a bit further. We're going to consider all of the various other invariants that we might want to include in a Lagrangian. So you can see here, I've got the first term, which is your scalar part of Riemann-Cartan. You've got all of these different quadratic invariants of Riemann-Cartan that you could include, and you've got all of the different quadratic torsion invariants. So I won't go up to cubic invariants and higher on the grounds of stability. We just choose not to consider these. And overall in the theory, you're going to end up with these 10-dimensionless coupling constants. So these alphas are going to sit in front of the Riemann-Cartan parts. and the betas are going to sit in front of the torsion parts. And there are 10 of these, and we get to vary them freely. So now we want to say, okay, well, how healthy is this theory? Can we impose some constraints on these coupling constants to make it a bit sounder? One popular requirement that we might want for a modified gravity theory is to say that it treats Minkowski space quite well. So Minkowski space should be a vacuum of the theory. If you take away all of the matter sources, the theory should have this Minkowski vacuum. It should be unitary on that vacuum. And you might also want the theory to be renormalizable on Minkowski space as well. So, famously, Einstein's theory is not apparently renormalizable if you just look at the powers of momentum that appear in the propagator. So an interesting question to ask when you're building a modified gravity theory is, well, is it going to be power counting renormalizable in this sense? Is it going to be apparently better than Einstein's theory on Minkowski background? So if you want to do any of these things, you really need to look at the propagator of the theory. We'll start with the linearized propagator. So linearize the theory on a Minkowski background in the absence of matter. If you want to get the propagator out, that becomes difficult if the 10-dimensionless coupling constants in the theory obey certain conditions. And the reason for that is because the Lagrangian becomes singular. You can't invert it to get the propagator. You have to do some special tricks in each case. So some colleagues of mine have studied this question quite deeply, and they found that there are nearly 2,000 distinct cases of the 10-parameter theory where you have to treat it separately. And those cases are going to be defined, as we'll see on the next slide, by some conditions amongst the dimensionless coupling constants. Of those 2,000 cases, it turns out that 450 of them can be made to be unitary if those couplings obey certain other equalities or inequalities. And then 60 of those, or nearly 60 of those, apparently are power counting renormalizable. So this is a good start. We'll take a subset of those 60 theories and then see are they actually interesting. So this is the subset, and you can see in the first column of this table, I've got the constraints on the couplings that define the different cases of the theory. So these are just linear relations amongst the 10-dimensionless coupling constants. In the second column, I've got these conditions that we impose on those couplings to make the theory unitary. Then in the final column, we have some estimates of what the particle spectrum would look like. And the nice thing about this is that we do find a few theories which have a pair of massless degrees of freedom, which you could tentatively associate with the two polarizations that we would expect to find of a graviton nature. Beyond those two massless modes, the only other degree of freedom that we get in these theories is sometimes we get a massive pseudoscalar particle emerging as well. So the main point to take away from this table is that all of the theories that we examine, where we require this unitarity, this power counting renormalizability on a Minkowski background, they all have this alpha naught equals 0 constraint. So they remove the Ricci scalar from the Lagrangian. So the Lagrangian is just going to be quadratic in Riemann, Partan, and Torsion. So we're going to look at the cosmology of these theories. See, is it going to be a reasonable expansion history for the universe? So we throw in an ansatz for the tetrads. Remember, the tetrads are the square roots of the metric. Then that's just going to be the FRW background. So I've left in this ansatz the spatial curvature K can vary freely. So we could have open, flat, closed universes. Apart from that, it's just going to be a straightforward FRW. And then for the torsion tensor, we need an ansatz as well. So in cosmology, we would want the torsion tensor to be isotropic. That restricts it to have just 2 degrees of freedom left in it. So we've got this scalar degree of freedom U and a pseudo-scalar degree of freedom called Q. And then on top of that, we'll throw in some matter as well, the sort of matter that you might expect in a cosmological model. So it's going to have equation of states, pressure is equation of state parameter times density. So for radiation, that parameter would be 1/3. For matter or dust, it would be 0. And then for dark energy, you would expect it to be -1. And we'll minimally couple those matter sources to the theory. So From the 10 parameters in the full theory, it turns out that if you're just studying the background cosmology, there are only 5 combinations of those 10 parameters that actually matter. And those are going to be the sigmas, which basically they control specific combinations of the quadratic curvature part in the Lagrangian, the 2 upsilons, which control the quadratic torsion part, and then alpha naught, remember that's in front of the Ricci scalar term, the Einstein-Hilbert term in the Lagrangian, that's going to have its own effect, so that sits there on its own. So that's 6 cosmological parameters in total. And then the background equations of motion, you can see that they're just going to be populated by those parameters. So all of the background equations can be written in terms of those reduced set of parameters. And these are obviously some very horrible equations, so we won't get too into these, but something that you can notice is that if you impose 2 very simple constraints on the general 10 parameter theory, so you switch off alpha naught and sigma 3, that is to say you remove the Einstein-Hilbert term from the theory and you remove a specific combination of the quadratic curvature terms, then the spatial curvature drops out of the cosmological equations completely. So the universe could be flat, open, or closed, but that wouldn't affect the expansion history and it wouldn't affect the evolution of the torsion. So we'll come back to that in a couple of slides. But in the meantime, we can basically map all of the theories that we had into different cosmologies based on these new couplings. We find on the right-hand side that we discover some results from the literature. On the left-hand side, this sort of cube shape of new cosmologies, these have not been considered before. So we'll pick, and the other thing about these new theories is they all have this property of eliminating the spatial curvature. They've all got the alpha naught, sigma 3 switched off. So we'll just pick a theory which is not too constrained that it's going to be very boring, and it's not too unconstrained that it's going to be not tractable to actually deal with. So I've just highlighted that here. It's got some very simple constraints imposed on the 10 parameter theory. Alpha naught, sigma 3, epsilon 1, all vanishing. And we'll look at the actual cosmology of this. So it turns out that the cosmological equations of motion reduced to a Friedmann-like equation, which is the sum of the cosmological densities, these omegas, is equal to some function g of both the Hubble number and the torsion. And then you get another equation in the torsion and the Hubble number. But what you can notice is that if your if your cosmology has matter in it with a particular equation of state parameter, then basically this g function is going to be going to a constant which depends on that equation of state parameter. And so if a particular source out of the various cosmological sources, matter, radiation, dark energy, if one of those is dominant, then this equation is going to go over to sum of cosmological densities is equal to a particular constant. So it's going to be a flat Friedmann evolution at that point. So I won't get too involved in what happens in general here. And, you know, in general, it's quite complicated. You effectively get you can see it from this equation. Sum of cosmological densities is equal to a constant. This is going to be a flat Friedmann solution where the gravitational constant gets renormalized depending on which equation of state parameter is dominant at that particular time. In the general case, that's quite complicated, but it turns out that of the remaining free couplings in the theory, you can pick a ratio of 2 of them equals to 1, and that has the effect that no matter which fluid is dominant, you're always going to get a flat Friedmann solution out. So you can see in this right-hand plot here, this compares very well against lambda CDM expansion history. So we've got flat lambda CDM expansion coming out of the theory, despite the fact we got rid of Ricci scalar and it can't see the spatial curvature. It turns out you can perturb that solution at the background level, and if you do that, then the only other thing that you get in the theory is you get a flat Friedmann solution of the physical matter plus an effective matter component. And that effective matter component is going to have an equation of state parameter which depends again on the dominant equation of state parameter. So it turns out that this is only important when physical radiation is dominant in the universe. A perturbation of the flat lambda CDM solution will look like you have extra dark radiation present. If matter or dark energy are dominating, then the perturbation is actually going to go away very quickly. And so this is only something which is important at early times, and you can use it to tune the early expansion history. So you can see on the right-hand side here, relative to lambda CDM, we can increase or decrease the Hubble number just by imposing a boundary condition on the equations of motion. So that would presumably be set at the reheating epoch. When we found this, we were quite excited because, of course, we have this, this Hubble tension problem. And one of the earliest solutions to the Hubble tension was supposed to be, okay, you increase your number of relativistic degrees of freedom in the early universe, boost the early expansion rate, and then the inferred expansion rate is going to be proportionally higher if you want to keep the structure of CMB the same. Of course, this doesn't fully solve the problem. It's also it only alleviates the tension. It's also in danger of colliding with the thermal history. So this won't be the full story, but it's still quite interesting. So I'll take a step back now from the new theories that we had, these 33 theories of the 58 of the 450. And I'll say, well, what are the general consequences of imposing torsion on cosmology, including torsion? Well, in the 10-parameter theory, this Lagrangian is pretty opaque. Just by looking at it, you couldn't really make any claims about what you would expect your cosmology to do, which is a bit of a disaster for someone who's interested in phenomenology and so forth. But something to notice is that by including torsion in general, all you're including are these 2 degrees of freedom in the background. You've got this scalar U and a pseudo-scalar Q that we had before. So from these, it's tempting to define a pair of scalar fields, so psi, phi and psi. And the way we've defined the phi field is a bit involved, but basically it just guarantees that these scalar fields, phi and psi, they're going to be conventional scalars. So if you do a conformal transformation, they're going to transform homogeneously, as you might expect to a pair of scalar fields in a gravitational theory. So what we want to do now is we want to say, okay, can we build a scalar tensor theory without any torsion in it whatsoever? So just using a metric and a pair of scalars, such that the background of that theory is exactly the same as the background of the full quadratic torsion theory. So the only way really to do this is by matching the equations of motion. It turns out that it is possible. So in order to build the scalar tensor theory, we're going to have at our disposal Riemann curvature, the scalars, and also their kinetic terms, which I write with an X. The torsion theory, remember, was built with these quadratic invariants of Riemann-Cartan curvature and torsion. So you come up with an ansatz for your scalar tensor theory. Something obvious to pick is just this extension of the Horndeski theory. So the general scalar tensor theory, but with 2 scalar fields. It's called Multigalileon. It's not the most general version you can pick, but in common with Horndeski theory, it's got these arbitrary G functions in it. And you would think, well, those functions are probably going to be polynomials, right? It turns out that that's not true. You can't replicate torsion by those means, at least not with polynomial G functions. So the way you end up doing it is you end up putting down a general Horndeski-like ansatz, but you introduce this vector B and another scalar chi, and these are going to be multiplier fields. You can get rid of them at the level of the Lagrangian, but you do so at the expense of those G functions being polynomials. So this is the final result that we get. And to just re-summarize, what we've done here is this is a scalar tensor theory without any torsion in it whatsoever, which replicates the cosmological background of the general torsion theory. So this is quite complicated, and I'll just quickly go over the anatomy of this. First thing to notice is that it wants to be interpreted in the Jordan frame. So these scalars sit in front of the Ricci scalar here. That Ricci scalar is actually the only incidence of gravity in the whole theory. So remember, we started off with a quadratic curvature in torsion theory that maps to a scalar tensor theory, which is just linear in the Ricci scalar. So that's quite odd. Another thing to notice is that the factors in front of the kinetic terms of the scalars and in front of those non-minimal couplings to gravity, those differ by factors of 12. So these are going to be conformally coupled scalar fields in the theory. And the big feature of this is that it's a non-canonical theory. So this was the price, again, that we paid getting rid of those multiplier fields. Basically, we've got this very ugly square root of some kinetic structure of the scalars appearing. And beyond that, we get some quite usual terms. So we get some mass terms for the scalar fields. And we also get some quartic potentials for the scalar fields as well. So those will obviously be very useful if we want to construct some inflationary models. The weirdest thing I think about this theory is that the alpha naught parameter, and remember at the beginning, the alpha naught in the torsion theory sat in front of the Riemann-Cartan scalar term. So this is the parameter that controls the Einstein-Hilbert term in the torsion theory. That does not sit in front of the Einstein-Hilbert term in the scalar analog theory. So we'll just drill down into the consequences of that. If you took a torsion theory which just had the scalar curvature term in it, so this is going to be the Einstein-Cartan theory from the beginning, and you ask what is the scalar tensor analog of that that reproduces the same background cosmology, you just get this horrible non-canonical scalar theory without any reference to curvature in it whatsoever. Bizarrely, this actually does turn out to reproduce the Friedmann equations. So you can get the phi equation out of this and substitute it into the metric equation that comes out of this, and it turns out that it does reproduce the Friedmann equations of cosmology, which is quite strange. And this theory is quite well known, this non-canonical theory. It's called Cuscuton. But it's not been motivated in this way before. So you can also do this with the teleparallel torsion theory. So this combination of quadratic torsion terms. This time the scalar tensor analog does turn out to contain a gravity term, which is just the Einstein-Hilbert term without any torsion. And you've got this extra scalar structure added to it. It turns out that to make teleparallel gravity equivalent to general relativity, you also have to switch off the Riemann-Cartan curvature using extra multiplier fields in the torsion Lagrangian. And the effect of that is basically to artificially switch off those scalars. So at the end of the day, the scalar tensor analog is just the Einstein-Hilbert Lagrangian, which is pretty much what you would expect, because that's obviously going to give you the correct background. You can also do this the other way. So you can ask, well, what kind of torsion theory would I have to construct that would give me a scalar tensor theory that I'm interested in? So these are some fairly natural parameter constraints that you can impose on the quadratic torsion theory. And these are actually designed to give you the cosmological background of a conformal inflaton scalar tensor theory. So down here you can see this Einstein-Hilbert and then non-minimally coupled scalar field with this factor of 12 in here. So the way this works is actually another Cuscuton identity. So the scalar tensor analog contains this non-canonical structure again, but we can get rid of it through another Cuscuton identity, and it all works out as being a very natural looking scalar tensor theory in the end. So returning to the theories that we had at the beginning, these new torsion theories, which are interesting as being unitary and PCR on Minkowski space. We recall that we had this theory here, which it reproduced the flat lambda CDM solution despite not having an Einstein-Hilbert term in it. And for any spatial curvature, it's going to give us the flat Friedmann expansion history. So we can now study the most general new theory that comes out of this map using this scalar tensor analog. So it's going to just have this pair of constraints on the general temperameter theory. The only difference in terms of the particle content between these two is that the theory we considered before just had the two massless modes that we thought might be a graviton. This more general case has an additional pseudoscalar, massive pseudoscalar propagating in it as well. So let's see, using the level of the cosmological background, what it can do. We get this quite messy scalar tensor analog. So what we've done here is we've shifted it from the Jordan frame. Remember, the analog is constructed in the Jordan frame. We've shifted it into the Einstein frame. And it just looks like Einstein's gravity and then a canonical scalar field. So you see it's got a canonical kinetic term and then some potential term. And then on the end, it's got this horrible cuscuton again. And the cuscuton is actually modulated by this omega of the canonical field, this function omega. And that function is interesting because it actually measures the degree to which the Jordan frame is deviated from the Einstein frame, which I've written down here. You can see that this potential is positive definite. And that's actually fixed by the unitarity conditions that were found right at the beginning of the talk. And that's interesting because if you have the positive definite potential, then you can think, well, that's going to act a little bit like a dark energy term. And that's exactly what it does in practice. So to see how it might do that, you can say, well, let's pick a really weird example, which is for the matter in the theory, we throw in a negative definite cosmological constant. This is the sort of thing that would never drive accelerated expansion in Einstein's theory, but it turns out that in this new theory, that's exactly what it does. It drives the de Sitter state, basically. Not only that, but the rate of the acceleration is not related to, sorry, the rate of the expansion is not related to the magnitude of the cosmological constant. It just depends on the ratio of the dimensionless couplings and whatever dimension you put into those couplings. So that's quite strange, and you can see that we check this numerically here as well. So in dynamical systems picture of the background evolution, this yellow region describes an accelerating expansion. The blue region is decelerating, and we've added a negative cosmological constant by hand. And you can see there's an attractor state in the accelerated region, which is very bizarre. If you want to pick something a little bit more conventional, you can add either no cosmological constant at all, or you can add a positive cosmological constant. So if you do that, basically there's another attractor solution which gets rid of that omega function, so that Jordan and Einstein frames coincide at that point. And remember, omega modulated the cuscuton, so it cancels the cuscuton. That has no effect. And omega going to zero, that corresponds to the canonical field being a particular constant. And so the kinetic term of the canonical field goes away as well. So all you have left is Einstein's gravity and this positive definite potential term. And so this is just going to be straightforward dark energy. Basically, if you put in a positive or zero cosmological constant, you end up augmenting the expansion rate by, again, some ratio of the dimensionless couplings in the theory. So that's quite nice. It's not, of course, a solution to the cosmological constant problem, because you see we've got a ratio of dimensionless couplings multiplied by the Planck mass has to equal something which is 10 to the 122 or whatever times smaller than the Planck mass. So we can't use this to completely account for dark energy, but it's still quite a nice feature to observe. And I should also add that this theory, this more general case here, this actually inherits all of the other good properties of this theory down here. So we've still got the flat Friedmann solutions. We've got the option to add this dark radiation tuning in the early universe. And now we've got a way to modify the amount of dark energy as well. So at the level of the background, theory actually looks really, really nice. But now we'll actually talk about some quite serious problems that we can get. when we go beyond the level of background and start including things like perturbations. And these are problems that are going to be generic, not just to theories with torsion in them, but more generally to high spin theories of gravity. Effectively, the problem has to do with the fact that right at the beginning we said, okay, let's take flat space and require that our theory is unitary on that space, so it's not going to have any ghosts or tachyons. And that's also required that power counting renormalizable. But we only did this for the linear theory. Now, power counting renormalizability, it's not the end of the world if the theory doesn't seem to be renormalizable. I mean, Einstein's theory is pretty popular. It's obviously not renormalizable in that sense. Maybe it has some other redeeming features. So you would search for some UV completion of that theory, or you might say, well, are there going to be fixed points in the renormalization group flow that save this? But at the end of the day, it's not a deal breaker if your theory doesn't appear to be renormalizable. The real problem, however, is that we only examined unitarity in the linearized theory. So it turns out that if you take these theories and you say, well, what happens when the fields become particularly strong, you can actually get unitarity broken in that context. You can get instabilities which develop. So this is associated with problems such as strong coupling. And to deal with these, really, you need to perform the Hamiltonian analysis on the theories. So Hamiltonian analysis of the general torsion theory, it's fairly similar to how you perform it for Einstein's gravity. So if you just take the fundamental moving parts of the theory, which are going to be the tetrads and the spin connection, in the same way that the metric contains 10 degrees of freedom, the tetrad and the spin connection contain 40. But of course, from the metric, you have to take away 8 of those for gauge reasons, right? Because you have your diffeomorphism invariance of the theory. So for the torsion theory, we don't just have diffeomorphism invariance, we also the gauge symmetry of the theory is the full Poincare group. So of those 40 degrees of freedom, we actually take away 20 of those. And so we only have 20 degrees of freedom that could at most be propagating in the theory at the end of the day. And those are accounted for by 2 polarizations of a massless graviton. So that gives us 18 left. And those 18 are distributed amongst extra particles that we might expect to occur. And those particles can be scalars, vectors, or tensors with positive or negative parity. So if you add up the multiplicities of all of these particles, it's 20. And these extra particles that occur only when you include torsion in the theory, these things are called tordions or brotons. So when you're actually performing the Hamiltonian analysis, basically you end up with these 30 fundamental degrees of freedom at the level of the fields, which you would then break down into all of these irreducible components. The way we do this is using these things called these phi functions. I won't get too into the motivation of the phi functions, but all you need to know really is that they each represent a particular spin parity part of the theory, and they all generically have this form of phi is equal to momentum plus a field-dependent term, which could either be the Riemann-Cartan curvature or the torsion. So in defining what the momentum is of the theory, the canonical description of momentum in the Hamiltonian picture is to say, well, momentum is going to be partial Lagrangian by partial velocity of your fields. But these definitions can carry with them implicitly the statement that some of those phi functions are actually equal to 0. And so we call these things primary constraints on the theory. And the way we deal with them in the Hamiltonian is to say that the total Hamiltonian is equal to canonical Hamiltonian minus multiplier times whichever of those constraints are primarily, whichever of those fields are primarily constrained. So this is the constrained Hamiltonian picture. It's not enough, however, to just ask that those phi functions be constrained with multiplier fields. Not only do they have to vanish, but as you evolve the theory, you have to have those phi functions having zero velocity, because otherwise they could start to not vanish, right? And so if you ask, okay, what do we need in order for the velocity of those primary constraints to vanish as well? We need the integrand of this term, this quality here to also vanish. So the implications for this integrand vanishing are dependent on whether or not the commutator, the Poisson bracket between whichever phi constraints you're dealing with, and all of the other phi constraints in the Hamiltonian, whether or not that bracket vanishes. So if it doesn't vanish, then you can use this equation here to solve for one of the multipliers u. If it does vanish, then this entire second term here vanishes, and you then need the first term to vanish for this this whole integral to vanish. So this first term vanishing is basically another constraint. We call this a secondary constraint, and then you have to repeat the process of requiring its velocity to vanish as well. And so this process goes on and on and on until finally you run out of constraints and everything should be consistent. And at that point, you say, well, how many degrees of freedom do I have left in my theory? Depending on how many degrees of freedom you have, you can associate those with the particles which might be propagating in the final theory. Okay, so this is the constrained Hamiltonian analysis. It's also called the Dirac-Bergman algorithm. But you can see, this is probably the most important point, you can see that what moves in the theory and what doesn't move is strongly associated with the commutators of the Poisson brackets between the primary constraints, these phi functions, and there were 10 of those that we defined. Okay, so these commutators between the various primary constraints, from this we construct the primary Poisson matrix. So the number of, the dimension of that matrix is going to be however many primary constraints your theory has. And the criterion for the health of the theory, going beyond the linearized unitarity power counting normalizability criterion we had earlier, the criterion that we'll introduce is that the structure of that matrix shouldn't change as you go from the linearized theory to the nonlinear theory. And the reason for that is because if the structure changes, then you're in danger of the final degrees of freedom in your theory being different between the linearized and nonlinear cases. And so then you have to go back and ask, well, these fields that we've activated as we went from the linear to the nonlinear case, those fields could be associated with many different pathologies. So they could be ghostly, they could be tachyonic. And there's also a more controversial consequence of having changes in the structure of the primary Poisson matrix as you have the different propagating fields taking different values. That's thought to be associated with some acausal behavior, but that's less well established. But basically, we take here's a selection of 8 of the theories, this big list of theories that we had right at the beginning of the talk. We examine the primary Poisson matrices of all of these theories. So you can see on the tops and the sides of these matrices, these are the phi functions that are primarily constrained in the theory. And these are also defined, of course, by which of those dimensionless coupling constants you switched off and on, and which take different values, et cetera, et cetera. That's where you get these primary constraints from. And then the entries in these matrices are going to be the commutators between those constraints. You can ignore basically what these dotted boxes and these crosses do. Basically, they have to do with whether or not mass parameters are present in the theory, but that's not so important. But the important thing to note here is that the dot in the matrix represents that commutator vanishes. And so you can see that in the linearized theories, none of these primary constraints have any commutators whatsoever. And so the Poisson matrices are completely trivial. But as you go from the linear to the nonlinear theory, still on the Minkowski background, but now without any notion of linearization whatsoever, you can see that suddenly Many of these matrices have lots of entries in them. So these entries, they schematically represent some long expressions depending on the field momenta in the theory. And this is a bit of a catastrophe, right? Because this indicates, that the primary Poisson matrix, you can think of it as like the initial data for performing the constrained Hamiltonian analysis and finding out how many degrees of freedom are propagating. If the structure of these matrices is changing very wildly, then it's almost certain that we're going to get a very radical change in the behavior of the theory as we go from linear to nonlinear. So yeah, this is a real catastrophe, except for two of these theories. So you can see that as you go from linear to nonlinear, these theories on the bottom left, they actually preserve their completely trivial structure. These also turn out to fail for slightly different reasons. It turns out you just have to go one step further in the constrained Hamiltonian analysis. You have to look at the secondary constraints, and you also get some changes in the commutative structure at that level as well. So in all of these cases, effectively what you find is that you break certain gauge symmetries in the theory, you end up activating certain fields in the theory, and so you can then go and ask, well, are those fields definitely going to be bad? Turns out they almost all are. This is a more in-depth look at the actual structure of the Hamiltonian of the quadratic torsion theory. So you pick out the kinetic part of the Hamiltonian, which is this first term here. And it has this very big, complicated expression. The only thing you need to notice about this expression for the kinetic part of the Hamiltonian is that it's quadratic in these phi functions, and these phi functions that appear here are going to be the unconstrained phi functions. So you can generally define the phi functions, but only some of them are going to be primary constraints for any given theory. And those phi functions, remember, they had the structure phi is equal to momentum plus some field dependent terms. So you can see that these quadratic terms here are going to contain quadratic momenta parts. So basically what we've got here is a quadratic form in the momenta of the fields related to the kinetic part of the Hamiltonian. And so by looking at the signs of that quadratic form, you can determine whether or not those sectors, those spin parity sectors of the theory are going to be ghostly or not, because they shouldn't enter with negative kinetic energy. And at the end of the day, it turns out that, going back to the activation of these fields as you go from the linear to nonlinear theories, they all turn out to be associated quite generally with negative kinetic energy. So this is really bad news. So just to quickly summarize, and I don't know, Dan, how much time do I have left?
Probably a couple more minutes.
That's perfect. Yeah, I just got a couple of slides then. Okay. Yeah, so just going back to the actual status of these theories now, remember that we had we picked out a couple of these that had really promising and interesting cosmologies. So what have we done with this Hamiltonian analysis? Well, so far we've tested 8, and they all failed for various reasons. Only some of those actually appear on this map. Only 6 of them appear. But you can see that they effectively rule out certain other sectors of the map. And so what we're involved with doing now is we're trying to sort of move the process to the west and to the north of this map to try and make contact with the theories that we're interested in, and seeing if these theories also have pathologies when you go to the nonlinear and perturbative levels. So the way we're doing this, I should also mention, is we've built some software that can perform the Hamiltonian analysis, which can be generalized, not just it's not just specific to torsion theories. You can generalize it to other geometric theories of gravity as well. So this is built for Mathematica. So to quickly summarize what we've done, we had this 10 parameter quadratic torsion theory, which is supposedly one of the more general theories that you could build, which has torsion in it. If you just look at the linearized theories on a Minkowski background, well, There's this big long list of theories which appear unitary and power quantum generalizable, which is very nice. And so we say, okay, do these actually have viable cosmologies? And it turns out yes, despite the fact that those theories don't have Einstein-Hilbert terms and they seem to ignore the actual spatial curvature, the cosmological backgrounds of those theories is really quite intriguing. So it's exactly what you would want from lambda CDM. You have the option to tune the early expansion history, and you also have the option to change dark energy content. Something I haven't mentioned in this talk, and this is actually not the preprint stage yet anyway, the theories that we looked at and found they had good cosmologies, they also contain Schwarzschild vacuum and can support plane gravitational waves as well. So this is really fairly promising, just at the level of these exact solution checks that theories could be very interesting. And we also have this general mapping that reveals the effect of torsion on the cosmological background, this biscalar tensor theory with lots of interesting phenomenology in it. But at the end of the day, you have to go from the linear to nonlinear regimes, and you find that there are these many problems that you have to overcome to do with activated fields not being at all healthy. So yeah, that's still work in progress. All right, I think I'm probably done then. I do have a bunch of extra slides, but I think it's probably a good place to